Okay, I think I mislabeled somewhere along the way, but this should be the beginning of 1.7, the intermediate value theorem. And this is probably the most, how do I want to phrase it? Definitely an important theorem, so much so that in math, when you see IVT, you automatically know that we're talking about the intermediate value theorem. Now, there's a couple things that need to be stated before kind of going through all of, like, what does it really mean? So first of all, anytime you say that IVT applies, the intermediate value theorem applies, is first of all the function, maybe I should start with, if some function is continuous, that's why we did the lesson on continuity, on some interval. Now, I don't know what those intervals are, so I'm just going to give a blanket statement from A to B. Now, it has to be a closed interval. It only works if it is a closed interval, so it has to equal A and equal B. And there's some value between some y value between f of A and f of B, or because it doesn't, like, this is saying that this is an increasing function, which we haven't really talked about yet. It could also be a decreasing function. So one of these two situations. Then, because this is your conditional, then there must exist a x value. I'm just going to write a value for x such that x equals c that satisfies that f of x, that f of c must equal that L function. So let me give you a quick visual. At any time, feel like you can pause. Let's say you had A right here and B. Now remember, it's continuous from A to B. So A and B are x values. Now, I don't know where f of A is. Maybe f of A is up here. I think that's where the picture is. So what that means is it's defined, so it's a closed. Maybe the function goes up, back down. And now remember, it's continuous. And let's say right here, this value is f of B. So basically, my picture is this example. Is f of B is smaller than some L value, which is smaller than f of A. So let's say you want to make L this value. And again, this inequality is satisfied, that L is between f of B and f of A. Well then, as I go across, because this function is continuous, remember in pre-calculus we said it's continuous if you put your pencil on the page and you never leave the page, then there must be a C value right here. Hold on. I knew I was missing something from my definition, that the C value must be between A and B. Then there must exist a value for C that equals X on the open interval. So on this open interval, so C needs to be between A and B in order for this to be the intermediate value theorem. Now, notice that I said there must exist. Can there be more than one? So let's call this C1. Well, over here in my picture, there's another example, so we'll call that C2. And over here, maybe there's another one. We'll call that C3. Now, you could have as many C's in the intermediate value theorem. All I'm saying is that there must exist at least one x value for C that's bigger than A and smaller than B based off of this theorem. And this is going to take some practice to figure out. So right now they're just asking you to investigate a few problems. So as we look at this, so and there's basically two situations that this guy wants you to look at. So between -5 and 2, let's go with red. So -5 is right here to x equals 2 is right here. Well, there is a value where f of c equals 2, because if you draw a horizontal line at y equals 2, there is a value right here. Yes, where so c is about -4.4. I don't know. I'm just estimating that f of -4.4 equals 2. But the intermediate value theorem does not guarantee this value. And the easiest explanation as to why not, even though there is one that exists, is this is a discontinuous function. There's definitely a break within the bounds, I misspelled that, between -5 and 2. The other reason why, there's actually two reasons why the intermediate value theorem applies, is if you look at the y values for these, you would say, well, f of -5 equals 0, and f of 2, I didn't even realize it was defined up there. I could have actually found the actual value, but we don't need to, is equal to -2. And we were looking at this limit to equal 2. Well, is 2 somewhere between the lower bound of -2 and the upper bound of 0? No. So 2 is not within the bounds. So even though there was a value, it was not guaranteed by the intermediate value theorem. And I hope that makes sense. That it can still occur even though the intermediate value theorem does not guarantee a value. And the same thing goes with the next one, because if you look at from -1, I think that's right here, to 5, right here, and they're asking the same question, the c equal 2, well, 2 is up here. I'm just going to draw the horizontal line. Definitely the graph does not equal, so no, there's no such value. Now the reason is slightly different here. Does the intermediate value theorem guarantee a c? Well, no, it doesn't, because you didn't get a c value. Now, even though this is a continuous function, you do the same work as if you did, I think it's still called f. Yeah, if you did f of -1, I think that's -1/2. If you actually figure it out, props to you. And f of 5 looks like, what's that, -7/2? F of 5 equals -7/2. Same reason. 2 is not within these bounds. So the intermediate value theorem does not apply. Okay, so just a couple things to make sure that the intermediate value theorem applies. Again, get used to seeing IVT, is that the function must be continuous. On the closed interval. And the second thing is, since we've been using f, I'll just stick with it. F of c must be between your bounds. F of a and f of b. Now these are just variables. These are pretty commonly used variables, so don't shy away from them. But in another math book, they might use something different. They might name the function differently. Doesn't really matter. Okay, so in this first problem, number 1, is this a continuous function? And the quick answer is it's not continuous everywhere, but we don't care about everywhere. We only care about this. So as you recall from pre-calculus, we had the domain issue of the denominator cannot equal 0. So x cannot equal -2. It's continuous everywhere else. So this -2 is not in the interval, so it is continuous on the closed interval. We're good so far. So now what you need to do, so it's like part 1 of this, check that it's continuous. Figure out what the left endpoint is, f of -1. So as you plug in -1 in for x, we get -4 in the top. -1 plus 2 is 1 in the bottom, so we're looking at -4 there. Let me leave a little bit of room to figure out what f of 3 is. So f of 3, you get 0 on top over 5. Well, 0 divided by 5 is still 0. And so the question would be, is 2/3 squeezed between these two values? And then your quick answer from there is the intermediate value theorem does not apply. So then the next problem that we're looking at is actually really straightforward, because if you look at your interval, and it's actually the same problem. You look at your domain, the denominator cannot equal 0, so x cannot equal -2. Just stop right there, because -2 is within this interval, and therefore it is discontinuous on the interval. So therefore the intermediate value theorem, IVT, is what I was about to say, again does not apply. I think this is a good place to pause the video, and I will catch you back up with the next video and finish the notes.